Hello everybody and welcome to this video. Today we're going to start talking about power and energy and why they matter in the field of electrical engineering. So if you recall, we talked about voltage in the previous video, and the important thing to remember is that voltage is talking about potential difference between 2 points, and for gravitation it's kind of intuitive what it's talking about, but for voltage it might be a little more difficult. It's talking about the potential difference between 2 points in a circuit or any other electrical or a conductive object. So it's the amount of energy required to push a unit charge, basically. So it's going to be, the units are going to be joules per coulomb, and that's going to be called volts. And the equation that we had was to understand it was the work required to move a certain amount of charge. So that's what to remember about voltage. And for current, just to recall, the units are coulombs per second, and that is the amount of charges passing through a cross-sectional area of a wire or some other object per second. So that'll be dq dt. So let's remember these two basic electrical quantities, the current and the voltage. But we do have to remember now, we have to learn that these two are not enough in the study of circuits. There's another thing we need to worry about, and that is power. We got to think about how much power something can handle, how much power something is burning, and that is the energy. So power is the rate of change of energy per second. So let's look at these two light bulbs here. We have a 60-watt light bulb and a 100-watt light bulb. When we say these things, what we're meaning is that at every second, so let me write the definition of power. What that is the amount of energy you're using per every given unit time. So what it's going to be is the amount of energy consumed per unit time. And the units are going to be, I'm going to write it like this way. It's going to be watts, which is the amount of joules per second, which is watts. So now I'm going to do a quick mathematical trick here. I'm just going to multiply this side of the equation by dq over dq. And this is a completely valid thing to do because the ratio of this thing is going to be 1. So I didn't really change the value or anything of the equation. So that is a valid thing to do. So doing this, what I'm going to get is, what I can do is to rewrite dw over dq as a certain quantity, and dq over dt. And you can see that I can still cancel that, so it's still valid. So let's look at these now. Let's look at the equations that we had above, and what we get is that dw dq is just the voltage. So this thing over here is the voltage, dw dq, right, like this. And the other one, dq dt, is going to be the current. So what I end up getting as a result is that the power at any given time that is consumed or dissipated is the amount of voltage across an element multiplied by the current through that element. That's the basic idea that we need to get from this video. So that's our power. Now, a few things to talk about though is the passive sign convention that we talked about in the previous video. And it's very important because if you get this wrong, it's going to convey a completely different idea. So let's think about some element here. I'm going to draw two wire or two terminals here going into some element. So what we got to do is, the passive sign convention is defined this way. So we're going to have some positive side of the voltage drop, and the negative side, and then that. And what we're saying is that the current, if there's a voltage drop across this is some element right now, we don't know, it could be a resistor or anything, it could be a inductive load, resistive load, or whatever. So the current through this element must flow from the positive to negative, which makes sense. And this is the conventional current, remember. This is not electrons, this is protons going from the higher voltage to the lower voltage, which is equivalent to saying electrons are going from negative, the lower potential, to a higher potential. As we talked about in a previous video, those are the same equivalent things. So the passive sign convention says that if you have a positive voltage drop across the element and there's a current flowing from the high to low, just like for example, a mountain or a reservoir of water where there's a gravitational potential energy, and you have some water flowing from a high gravitational potential energy to a lower potential energy. So here's a higher one and here's a lower one, and there's our current going here now. We can call that I2 just for illustrative purposes. So that is going to be a positive power. So we're going to get a positive current times a positive voltage, which is going to be a positive power. What that's talking about is the power consumed by this element. So the power that the energy per second that this element is using up. So for example, if we have, let's just give some numbers here. If you have 4 voltage drop across this element or conductor that is 4 volts, and you have a current of 3 amps flowing from high to low here, what we're going to get is 4 volts times 3 amps, which is equal to 12 volt amps, which is just going to be, we're not going to use 4 volt amps now, but we'll do that later on to distinguish real power from a different kind of power. So what's this going to be is, if you remember, voltage is joule per coulomb, and ampere is defined as a coulomb per second. So we get joules per second, which is 12 watts. So as long as at every instant you have 4 volts and you have 3 amps flowing through this element, the element is consuming 12 watts of power here for this particular element with these numbers. So what about a different scenario? What if we have the same or a different kind of element, and let's see here, we have that going, and what we have instead here now is a positive, negative, same voltage drop, but then the current, the conventional current, instead of flowing from high to low, is flowing from here to the high potential. Kind of like if you have high potential to low potential on a mountain, but then the current's flowing upwards. So what that means is something is supplying energy to go against the path where the electrons are going to be at a lower potential, lower state of energy. So basically what this kind of tells us is that something is supplying energy to this. So, and that kind of makes sense because it turns out that if you have a negative, if you have a current going against the passive sign convention, what you're going to have is power is equal to negative current, because it's going from low to high instead of high to low, which is the define the conventional current, that is positive to negative. If you have the opposite of that, you have a negative current going. So you're going to have a positive voltage, and you're going to end up with the multiple is going to be a negative power, which what that means then is that this element is not consuming power, it's supplying power. And if you look at it, it makes sense because the current is going here, and then showing up here. It's coming from the positive terminal, and if you think about it, a battery does the same thing. If you look at the schematic of a battery in a electric circuit, we have some resistor here, and I close the loop. This is the positive, that's the negative. The current flows from positive to negative, and that is basically what we have here. So the power is being supplied, so it's a negative, so that means the power is being supplied. So those are two key things to remember here before we do anything else, because those are pretty important and we can't misinterpret it. So another thing to look at is the conservation of energy, which says that the sum, oops, let's use a white color here. Nothing against the blue color, but it's better here. So the sum of the power must equal 0. The power for each element in a circuit. So you got to make sure that when we doing these, because remember we said that there's the change of magnetic flux. That's the assumption that we made in the first lecture. That is equal to 0, meaning if you have some circuit with some elements in it, we're assuming that the only energy supplied to the circuit is the voltage source or some current source, and not some external change in the magnetic flux that can induce a voltage across the terminals. We talked about that in depth in some previous videos. Because of that, because there's no external signal or anything like that, or we're assuming, at least in this class, to simplify things, there's no external signal inducing any voltages and giving us energy from outside the system, the sum of the power dissipations or absorption of any element in here must equal 0. The total change must equal 0. And let's see. And another thing to remember, though, is the integral form of the work done, which is that the integral from initial time to final time of power with respect to time is going to be the integral from initial time to final time of the voltage times the current with respect to time. So that's one thing to remember, and that's the energy that is consumed or dissipated for a given element. If you want to get into the physics of it and do all that stuff, you can use this. And keep in mind, the reason I'm going to the depth with these and doing the math and the physics of it is because as an engineering event, you have to understand these fundamental principles, or else you're bound to make some kind of mistake or being unable to do some kind of diagnostics on your circuit if you're not familiar with these basic energy, voltage, current, power relationships and concepts. So another thing is to remember is a watt hour. So a watt hour is something that the electric power utility companies use. A watt hour. If you remember, a watt has units of joules per second, and hour has a unit of let's say seconds for this case. You can turn it into seconds. And a watt hour then is the total amount of energy used. That's what we're going to get with a watt hour. So let's see. What I'm finding in my book is that 1 watt hour is 3,600 joules. So we're going to keep that there for the problems that we're going to do. And the reason for that is 1 watt is 1 joule per 1 second, and 1 hour is let's see, do a quick unit conversion. So you have 1 hour here, you have 60 minutes per 1 hour, and what do you have? You have 60 seconds per 1 minute. So let's see, hours cancel out, minutes cancel out, and we end up with seconds. So what we end up getting is that 1 hour, and we already noticed, but I'm just going to go through it to show you a good practice of doing a dimensional analysis. And we get 3,600 seconds here. So if you multiply 1 hour by 1 watt, we get 1 watt hour, which is 1 joule per second, multiplied by the 1 hour, which is 3,600 seconds. Seconds cancel out, and you get what we got above, 3,600 joules. So that's 1 watt hour, as we got above here. So in the next video, we're gonna talk about or do some problems regarding power and current and voltage. And let's see, is there anything else that we need to go over besides that? So here is the work that is done, the total energy that is spent for either supplying power or absorbing power. And over here we talked about the signs. So if you have the current, let's see, if you have a voltage drop across an element like this, that means a voltage drop, current must be going in this direction from the high to low, kind of like a high point, like a mountain, and the gravitational potential energy is going to pull this current from the high potential to the low potential, assuming that the low potential is ground. So let's see, anything else in here? Okay, so knowing what we learned, now we can look at these bulbs, and we can see that it kind of makes sense, because now we can say this bulb uses 100 joules per second and this bulb uses 60 joules per second, and we can see that this one uses more energy per second, and that's kind of the mathematics that we went through and the physics kind of help us better understand what's going on there now. I'll see you guys in the next video.